Section 2.3 is on page 39. Talks about modeling with first order equations. So we're going to focus on one application, mixtures, liquid mixtures specifically. This could apply to different economic mixtures and, some other applications as well, but we're going to focus mainly on liquid mixtures. So what we're trying to do, we're trying to measure the amount of substance in a liquid mixture at any given time. For example, we're going to focus on sugar, specifically sugar in a can of soda. So the can contains a lot of liquid. Not all of it is sugar. We're just going to focus on, we're going to let Y or Q depending on the problem. Probably I'll stick with Y. To be the amount of the sugar in the substance, or in the liquid or whatever it is. So we start off with the mixture. We are looking at the amount, the rate of change of a substance Q. That's the amount of acid, amount of dye, depending on what you're doing in a tank. So the rate of change will be dq or dy dt, depending on what you choose the variable to be, is equal to the rate at which Q flows in minus the rate at which Q flows out. So basically, this is the equation that you have to remember. dq dt would be the rate of Q entering and the rate of Q exiting. And I'll do a couple of examples to really show that. We're going to look at page 47, number 1. Consider a tank used in a certain hydrodynamic experiment. After one experiment, the tank contains 200 liters of dye. So we have initially 200 liters of dye with a concentration of, times the concentration, 1 gram per liter. So we actually have 200 grams of dye in the mixture. So it's 200 liters, but it only contains 200 grams depending on the concentration. Of course, anytime you want to figure out the amount of a substance, take the quantity, that is the liters, the milliliters, whatever units they're using, the gallons, and multiply it by the concentration. To prepare for the next experiment, the tank will be rinsed with fresh water. Okay, water is neutral, it has zero of any substance, that's the assumption. And it flows in at a rate of 2 liters per minute. And the well-stirred solution, that's always the assumption, is that any time at any given time you are taking any sample of that mixture, the concentration is the same all throughout. So it's not like a cup of coffee. When you drink, the top is a bit bitter, and when you get to the bottom it's really sweet. It's like a can of soda. Anywhere you drink from the soda, the concentration of sugar, say, will be the same. So, and it flows out at the same rate. So if I let Y equal the amount of dye, basically the grams of dye in the mixture, Y sub 0, I already got it to be 200 grams. That's what I started with. And if I take dy dt, the amount, the change of rate of the amount in the mixture at any given time is the rate in minus the rate out. So this is a bit different. Oh boy. Here we go. So dy dt, and let's see how this works. The rate in, we're letting in 2 liters every 1 minute. And the concentration that's going in is water. It has 0 grams per liter of that substance, minus the rate out. The rate out is also 2 liters in this case per minute. The concentration, well, we have 200 liters in the tank. Since you're putting in 2 and taking out 2, that substance, that amount of liquid is not changing. However, now the concentration is how much is present divided by 200. That will be the concentration at every given time. Once you add the first drop of water, the concentration is going to be less than 1 liter per gallon because you're adding water. Kind of like having coffee and it's kind of sweet. You add pure coffee to it, and that will dilute the concentration because now you have more coffee than you had initially. And here we're going to have that amount of concentration at any given time. And once you set this up, this becomes either a 2.1 or a 2.2 problem, meaning it's either a separable problem or it's a linear equation. So this is 0, obviously, minus, and if I reduce that, that is simply y over 100. Now you have to drag the units. We'll talk about the units at the end. And since I have this equation, I can integrate. Actually, I rushed. This is a separable equation. dy over y will equal negative 1 over 100 dt. And now that I separated those, oops, didn't want to show you the next problem, but these things happen. Okay, here we go. And if I integrate, I'll get natural log of absolute value of y equal negative 1 over 100 t plus c, and y will equal e to the negative t divided by 100 plus c. So basically, y equal some initial amount. You could call it a, you could call it y naught if you wish, e to the negative t over 100. That's the equation. My goal is always to find y naught, and that's where the initial amount comes in handy. I should have copied that right there. Initially, I have 200 grams of the dye. So y of 0, I just want to warn you, it's not always that simple. This problem, since it's the first, it's really straightforward. Y naught or c, e to the 0, and that's 200. So I get y naught to equal 200. So now my equation becomes y equals 200 e to the negative t divided by 100. Now, give me any time you want, I'll plug it in, and the time has to be in minutes. I will tell you how much of the dye is present in grams. That's what y is measured in. Tell me how much amount you want in y, and I'll tell you how long it takes. So if I read the problem now and I figure out really what they want, that's basically what they want most of the time. If I look at what they want, find the time. So they want us to find t. Okay, find the time that will elapse before the concentration of dye in the tank reaches 1%. So let's set this in y. If I want the amount of dye to reach 1%, well, 1% of 200, because I have 200 grams, will be 200 e to the negative t divided by 100. And if I divide by 200 both sides, this is simply an exponential equation. And we know how to solve that because we did that in Math 5B, second semester calculus, over and over and over. And t turns out to be negative 100 natural log of 0.01. And if I throw this in my calculator, and you should get yourself a nice scientific calculator, if I throw that in, I will get that to be 460.52 minutes. You could convert it to hours if you wish. You don't have to. T will equal 460.52 minutes. And that's more than enough. And there it is. The next problem is in the handout. You could find the handout in the files. There's a handout for section 2.3 and answers. Just go into files and you'll see a handout folder. Open it and these problems are there. The reason for that, our book doesn't have enough problems and I just wanted you to have enough practice. So here it says, a tank with a capacity of 500 gallons originally contains 200 gallons of water. So let's say this is a tank. Let's say it looks like this. It doesn't have to, but because the shape is not going to matter. And it holds 500. Okay, that's the whole capacity. And initially it has 200 gallons of water. Now, since it has water, well, initially we have no amount, unless they say with 100 pounds of salt. Okay, they gave us the amount. So if I let y equal the amount of salt in the tank at any given time, and of course this is in, I'm sorry, this is kilograms. This is in pounds. So I know that the initial amount, y sub 0, is actually 100 pounds of salt. Alright, I got that information out. Let's go on. Water containing 1 pound of salt per gallon, okay, that's the concentration, is entering the tank at a rate of 3 gallons per minute. Well, let's see. The change of y with respect to t is the rate in minus the rate out. I think I have to space this a bit more. Okay. So the rate in, they already told us we have 3 gallons per minute. And we don't want the amount of liquid, we want the amount of salt at a concentration of 1 pound per gallon. So basically we're getting 3 pounds of salt every 1 minute. And the mixture is allowed to flow out, again they mix it thoroughly, of the tank at a rate of 2 gallons per minute. So you're letting out 2 gallons per minute. And the concentration is going to be what? Y divided by the volume. Well, let's see. I'm letting in 3 gallons per minute. And I'm letting out 2 gallons per minute. So the volume in the tank, initially you had 200 plus, and if I want to go by T, I am gaining 1 gallon every minute. So the amount is 200 plus T. That's the total volume. That's the concentration. This will be pounds per gallons as well, and gallons cancel out, and now the units match. And now we proceed to solve this equation. And here I'm looking at dy dt equaling 3 minus, again, these, oh no, they don't, never mind, minus 2y divided by 200 plus t. Now, this is not a separable equation, but what I could do, I could say dy dt equals dy dt plus 2y over 1, or, boy, come on. Technology. Y times 2 divided by 200 plus t equaling 3. This is a first order differential equation. This is a 1. That's very good. This is p right there. So now that I know what p is, I could come in and say, well, let u equal e to the integral of p, which is 2 divided by 200 plus t dt. And u will equal e to the twice natural log of 200 plus t. Properties of logs, make that to a power, and u will equal e to the natural log of 200 plus t squared. Those undo each other, and u is simply 200 plus t squared. Multiply this equation by u, and I'm really looking at 200 plus t squared times dy dt plus 2. If you multiply that here, that will be simply 200 plus ty equaling 3 times 200 plus t squared. And if I isolate dy, actually if I figure out what is it you multiplied to get that product rule? It'll be 200 plus t squared times y. There it is. And now, if I integrate, I'll be getting 200 plus t squared times y equaling, and the integral with respect to t is 3 times 200 plus t cubed divided by 3 plus c. So y would equal dividing, let's see, this is the same amount, so dividing a cube with a square will leave you with a 1 plus c divided by 200 plus t squared. That's my equation. I need to figure out the initial amount that's given. Y of 0 is 200 to the 1 plus c divided by 200, it's right there, 200 squared. And initially we said we had 100 pounds. So 200 cubed plus c equals, actually it's easier the other way, okay. So c over 200 squared, oh man, I think I need a new stylus, equals negative 100. Simply 200 minus 100. So c is actually negative 100 times 200 squared. And now my equation becomes y equals 200 plus t minus 100 times 200 squared divided by 200 plus t squared. And now either give me an amount, I'll tell you how long it takes, or give me time and I'll tell you how much you have. One of the two. Either they give me t, I find y, or they give me y and I find t. And here what they want, let's see. We finished down to here. It says find the amount of salt in the tank at any time prior to the instant when the solution begins to overflow. Well, let's see. How long is it going to take to overflow? Well, this tank holds 500 gallons, right? Initially it has to, and you're gaining a gallon every minute, so it's going to take 300 gallons. Since it's going 1 gallon per minute, the time is 300 minutes. In 300 minutes, it's going to begin to overflow. They want to figure out how much is present at that time. And let's do that. So now I am looking at, so it takes 300 minutes to fill the tank, and therefore y of 300 would be 200 plus 300, that's 500, minus 100 times 200 squared divided by, if I put 300 right there, that's 500 squared, and y would simply equal 500 minus, and after you do all the reductions, you'll get 448 pounds of salt. Got it. That's what they wanted. What else do they want? So find the amount of salt we just did. Now let's go with blue. And find the concentration in pounds per gallon of salt when it is on the point of overflowing. Okay, concentration, that's simple. Concentration is simply, we have 484 pounds of salt divided by, and we're going to have 500 gallons. So that is 0.96 pounds of salt per gallon at that given time. And if I go back and look at what else they want, compare this concentration with the theoretical limit concentration if the tank had an infinite capacity. What does that mean? That means if you were to take, and here, let me write it, theoretical concentration would be 200 plus t minus 100 times 200 squared over 200 plus t squared. That's the amount at any given time, right? Divided by 200 plus t. So this is the amount of salt, you guys, at any given time. And this is the volume at any given time, right? And if I split those, this divided by itself is 1 minus, and if I divide those, that would be 100 times 200 squared divided by 200 plus t cubed. Now, if I take the limit as t approaches infinity, because you're letting this run infinite, wouldn't this t in the denominator dominate? And that will approach 0, and you would be left with 1 pound per gallon initially, or ultimately, if you let it run for a very long time, we got it to be 0.96 in 300 minutes. Of course, theoretically, you'll never reach the 1 pound. You'll get 0.99999 divided by 1. Now, the homework, in the book, you're going to do number 9, and on the handout, you're going to do number 2, 3, and 5a. And that concludes this section.